All right, here we go. So for probability, our goal for today is to find probability of independent and dependent events. But before we can do that, we do need to talk about what basic probability is. So for a coin flip, a bunch of us have done this virtual coin flip, and we've gotten all different kinds of results, right? Some people got 5 heads and 5 tails. Some people got 6 and 4, or 3 and 7, or 7 and 3. I think that's the biggest spread that I've seen so far is 7 and 3. So when we're flipping a coin, if I'm flipping it 10 times, how many times would you expect to get heads? And how many times would you expect to get tails? Right, yeah, 5 of each. That's kind of what you would expect, right? That's called, so 5 out of 10 or 1 out of 2 if you reduce the fraction. That's the theoretical probability of flipping heads or flipping tails when you flip a fair coin. Yeah, so that's the theoretical probability. That's what you would expect to happen. What actually happens, like if you actually do an experiment, is called the experimental probability. So each of your experiments gives the experimental probability result. So if we take like Diego's results, he got 4 heads and 6 tails. So his experimental probability for getting heads is 4 out of 10. And his experimental probability for tails is 6 out of 10. So those are our different, that's kind of the difference between experimental and theoretical probability. Experimental can be different because it's based on what actually happens in the experiment. And usually experimental probability will line up with theoretical probability if you repeat the activity enough times. So if you continue to like flip coins, you know, thousands of times or something like that, if you do have thousands of coin flips, it should approach, you know, that 5 out of 10 or that 1/2, 50% of the time probability of getting heads or getting tails. So that's a quick exercise in theoretical versus experimental probability. So theoretical is the expected amount of favorable outcomes out of the total amount of possible outcomes. Experimental is what actually happens given an experiment. Okay, so hopefully that was a fun little intro / segue into what we're going to be talking about today, which is probability of independent and dependent events. So for our notes today. And today we are going to mostly be dealing in theoretical probability, not experimental probability, because actually doing a bunch of experiments takes time. So we're going to be, and that's the way most probability deals anyway, is in theoretical probability. Okay. So first of all, talking briefly about probability, kind of like we saw in our warm-up, what probability is. Basic probability is the number of favorable outcomes over the total number of possible outcomes. So when we were flipping a coin, you know, the number of favorable outcomes, if I wanted to know what's the probability of getting tails, well, then tails would be my favorable outcome. So that's 1 favorable outcome out of 2 possible outcomes, because you could get heads or you could get tails. So the probability of a coin flip landing on tails is 1 out of 2. Okay. So that's basic probability, and you've probably heard a little bit about basic probability before. You know, whether it's in terms of a coin flip, or if you were in elementary school and told to pick a marble out of a bag, and what's the probability that the marble will be green versus blue, red, purple, or whatever the other marbles were colored. So that's basic probability. Today, what we're going to talk about is probability of more than one thing happening. So this is going to be probabilities of compound events, or more than one event happening. So there's two different kinds of multiple events. There's independent and there's dependent. Independent is when they do not affect each other. Dependent is when they do affect each other. So we're going to talk about that next. So we're going to start with independent events. They don't affect each other. And I'm not sure if I used the correct effect there, but this is math class, not English class. We don't have to worry about it. So independent events don't affect each other. So some examples of independent events. If you spin a spinner multiple times, those are independent events. So spinning a spinner, flipping a coin. It doesn't matter how many times I flip the coin. That's not affecting my probability down the road. Choosing a card, or choosing something else, choosing a marble out of a bag, stuff like that. You're going to see this phrase with replacement. Or you might also see like, I choose a card and then I put it back and choose another card. That's that same idea as with replacement. So if I'm picking something out, putting it back, and then picking something else, that's independent events, because what I did doesn't affect what I'm going to do next. So those are some examples of independent events. And so here's how they work. When multiple events are happening, you multiply their probabilities to find the probability of both of those things happening. So here's the big important idea here. When multiple events happen, multiply their probabilities. When multiple events happen, multiply their probabilities. So we're going to go over a couple of examples and kind of go from there. Example number 1. In example number 1, I have a bag of marbles. Here's my bag. Looks kind of like a pomegranate. Oops. In my bag, we have 4 pink marbles. We have 1, 2, 3, 4, 5 blue marbles. If I can write with the blue pen. Whew. All right, and where's another color? Another one that's different enough. We'll do 4 yellow marbles, yellowish. They're a mustard yellow. Okay, so we have 4 pink, 5 blue, and 4 yellow. And we want to know the probability that I pick a pink one and then a yellow one with replacement. So that means I pick out a pink one, put it back, and pick a yellow one. Okay. I'll give everyone a moment to finish writing if you're writing. And then we'll talk about it. Okay. So what I want to do is figure out what's the probability that I'll pick a pink one, and then what's the probability that I'll pick a yellow one, and multiply them together. So the probability that I'll pick a pink one, well, there's 4 pink marbles, so that's my number of favorable outcomes. 4 pink. Out of how many total marbles could I pick? Well, there's 4 pink, 4 yellow, and 5 blue. If I add all those together, that is 13 total marbles. So that's the probability of picking pink. And then I want to multiply this by my probability of picking a yellow one. So if I put that back and I want to pick a yellow one now, there's 4 yellow marbles in the bag out of 13 total marbles. So that's the probability of picking a yellow one. And then I just multiply the fractions. So remember, when you multiply fractions, you multiply straight across. 4 times 4 is 16. 13 times 13 is 169. So this is my overall probability here. Okay. So that's the probability that I pick a pink one and then a yellow one with replacement. 16 out of 169. Okay. Any questions with that one so far? Okay. If you do have a question at any point, feel free to type in the chat or unmute yourself and say so. Our second example is going to use the same bag of marbles, so we're not going to redraw the bag of marbles or anything like that. Why reinvent the wheel? Second one, this time we want the probability that you pick a green one, or not a green one, pick a yellow one. Ugh. And then a blue or pink one. With replacement. Probability you pick a yellow one and then a blue one or a pink one with replacement. So what we want to do is take the probability of picking a yellow one and then multiply it by the probability of picking a pink one or a blue one. Okay. So in the chat, what's the probability of picking a yellow one? What's the probability of picking a yellow one? Yeah, it's the same as it was before, right? 4 out of 13. Because there's still 4 yellow ones and 13 total. What's the probability of picking a pink one or a blue one? Nice, Shy. Yes. We have 4 pink and 5 blue. So if I'm okay with picking either one of those, that means there's 9 total that I would be okay with picking out of 13 marbles. And then we just multiply those. 4 times 9 is 36. 13 times 13 is 169. And this fraction doesn't reduce. If your fraction does reduce, you should reduce it, but that one does not. Okay, so that's probability with independent events, events that don't affect each other. So each time we're just thinking, how many ways are there to do what I would like to do out of how many total options we have? And then when there's multiple events, we're multiplying the probabilities so far. Okay. The next thing we'll talk about is dependent events, events that do affect each other. Okay, so dependent events do affect each other. For example, most dependent events are going to be things where we do them without replacement. So like I pick a marble out of the bag and then I don't put it back and I pick another one. Or I pick a card and I don't put it back in the deck and then I pick another one. So we're going to see the words without replacement. Or things like then I don't put it back. And so if you see the words without replacement or I did something and then don't put it back, those would be dependent events. So we're going to do the same kind of thing. You still multiply the probabilities. It just, your second probability is going to be affected by the first probability, by the first thing that you did. So here we go. For example number 3, this time instead of having marbles in a bag, we're going to have candy bars in a bag. So here's my brown bag of candy bars, as one has lying around the house. And we're going to have 3 Hershey bars in here, 2 Skittles. What else? We'll do Snickers. 3 Snickers. 4 Twix. A Milky Way. And 2 Reese's. So there we go. We have 3 Hershey bars, 2 Skittles, 3 Snickers, 4 Twix, a Milky Way, and 2 Reese's. Yeah, some good candy there. I'd be happy if it was Halloween and that's what I got. Okay. Let's see. Let's do, for our first one, we'll go basic. Probability that you pick a Twix, then a Reese's, without replacement. Okay. Let's see. How many candy bars do I have here to start with? 5, 8, 12, 13, 14, 15 candy bars. So since there's 4 Twix out of 15 candy bars, my probability of picking a Twix would be 4 out of 15. But then I didn't put the Twix back. I ate it because, you know, I'm picking candy to eat here. So probability that I pick a Twix and then eat it and then pick a Reese's. Well, there's still 2 Reese's left in the bag, right? But how many candy bars are left in the bag? If I ate one of them. Yeah, there's only 14 left. So my probability of picking a Reese's for the second time around is 2 out of 14. Because I ate one of the Twix bars. So then we multiply those. And we get 4 times 2 is 8 out of 15 times 14, which is 210. And this is a fraction that does reduce a little bit. So we should reduce it. They're both divisible by 2. I can divide the top number by 2 and get 4. I can divide the bottom number by 2 and get 105. So there's my reduced fraction for that one. Okay. All right, last example here, or last example, with this, before we move on to specific context of the homework. Example number 4, we're going to use that same bag of candy, but this time we want probability that we pick 2 Hershey's and then a Snickers. Or actually, we'll have this be the second to last example because there's one more thing I'd like to talk about. And we're going to go again without replacement because I'm still eating candy bars here. Okay. So this time we're going to have to take the first Hershey probability times the second one times the Snickers. Okay, so the first time I pick a Hershey bar, my probability is 3 Hershey's out of 15 total candies. The second time I pick a Hershey bar, though, I've eaten one of them, so there's only 2 Hershey bars left out of 14 candy bars. So if I eat one of them, there's only 2 of those left, and there's only 14 candy bars left. But then for the Snickers, there's still 3 Snickers in the bag. But now there's only 13 candy bars left in the bag because I've already eaten 2 Hershey's. So then we multiply straight across the top. 3 times 2 is 6 times 3 is 18. And 15 times 14 times 13, that one I'm going to have to use a calculator. That is 2,730. Okay. And this is another one that reduces. Both of these numbers are divisible by 6. So that reduces to 3 over 455. The ones that you have on your homework that reduce will reduce a lot more easily than these. Primarily because the samples, the amount of stuff in the bag on your homework is going to be less. So that creates nicer fractions. Okay. So the last thing I want to talk about we want the probability that we pick a Milky Way and then an Almond Joy. So we have the probability that we pick a Milky Way times the probability that we pick an Almond Joy. What's wrong with this? Do we foresee any potential issues here? Yeah, that's a problem. There is no Almond Joys. So what's my probability of picking an Almond Joy if there are none? 0. Yeah. So I can still take my probability of picking a Milky Way if I want. There's 1 out of 15 there. But it's times an Almond Joy, which is 0 out of 15 because there are no Almond Joys. So my overall probability is 0 because anything times 0 is 0. So just want to make sure we went over that. Anytime there's something is impossible, that would be a 0 probability event. So anytime you have something with 0 probability, even if there's other events also happening, your probability overall will be 0. Okay. Any questions so far? Any examples we want to go back to? Anything that's kind of confusing right now? Okay. If not, we are going to jump to the homework and kind of go through a couple of the problems there and then be on our way. So let's take a look at the assignment. It's going to be an IXL section. It's a 7th grade IXL because that's where a lot of the probability stuff is. I'm glad you're good, Faith. All right, here we go. So this is what our homework's going to look like in IXL today. You flip a coin twice. What is the probability of getting heads and then getting heads again? So the probability of, first of all, this is an independent event because flipping a coin and then flipping a coin again doesn't affect each other. But if we're treating them as 2 separate events, here's what we get. Getting heads and then getting heads again. So remember when we have 2 events, we have to multiply them or multiply their probabilities, right? So the probability of getting heads the first time was 1 out of 2, right? Because there's 1 heads on the coin and there's 2 possibilities. And then the probability of getting heads the second time is also 1 over 2. And so we have to multiply those. Yeah, so we get 1 over 4 as the probability of getting heads and then getting heads again. So when we talk about two events happening or two things happening in a row, make sure we take the separate events and multiply their probabilities. So 1/4 would be the probability of getting heads twice in a row. So we'd put, enter your answer as a fraction or a whole number, so 1/4. All right. There's a lot of card choosing ones in here. You pick a card at random without putting the first card back. That's important. Without putting it back signifies that we're dealing with dependent events. You pick a second card at random. What's the probability of picking an 8 and then picking a 6? Well, there's 1 8. So the probability of picking an 8 times the probability of picking a 6. There's 4 cards. One of them is an 8. So 1/4 is my probability of picking an 8. Because there's 1 8 out of 4 cards. But then if I don't put the 8 back, there's only 3 cards left. And one of those is a 6. So we get 1/12 for that one when you multiply. Okay, so that's the type of problems that we're going to see on our assignment for today. If you would like to see more examples, stick around and we'll do more examples. There's a couple of you that I would like to talk to real quick. Brianna, Luis, Cheyenne, and Ashlyn. If you could stick around for a moment, that would be great. Otherwise, you guys are free to head on out and work on the assignment. Or if you have questions, feel free to stick around.